All right, here we're going to look at the sum and difference rule for derivatives. And again, I'm not going to go through a formal proof, but relate this back to limits again, is that we know that the limit of a sum is the sum of the limits. And so in this case, the derivative of a sum is actually equal to the sum of the derivatives. Now, what does not work for derivatives and are not related is the product rule and the quotient rule do not work the same way. And we will be looking at those later. But the derivative of a sum is actually the sum of the derivatives. If you would like to see a proof, there is one in the textbook. At this point, I've proven the power rule, and that's all I really want to prove for this unit, or at least for this section. So example 5, it basically just means I'm going to take each derivative separately. And so to take the derivative of each of these, I could write this as the derivative dy. Let's see. I just want to rewrite this. That y should not be there because y is this function. It should be just d dx of 2x to the 6 plus x to the negative 9 plus 7. So what we have here is d dx of 2x to the 6th plus d dx of x to the negative 9th plus d dx of x to the of 7. And in the end, you really don't need to write this out the long way. You can just take the derivative of each of these individually. The derivative of 2x to the 6th is going to be 12x to the 5th, plus the derivative of x to the negative 9 is going to be negative 9x to the negative 10. Convince yourself that that is true. Plus the derivative of 7 is just a constant, and so it would just be plus 0. If I want to simplify my answer here, I would have 12x to the 5th minus 9x to the negative 10th. Again, we talked about the fact that if they ask you to leave your answer with positive exponents, you would rewrite that. Since the original had a negative exponent in it, I'm going to stop right there and leave it like that. All right, so now on these problems right here, the derivative of a product is not the product of the derivatives. It doesn't work. All right, we'll look at example B, and I'm going to do these for you. Instead of having you practice them, I want you to see each one of these done out. And so this first one is the derivative of a product, and there is a rule, but we don't have that rule yet. We haven't done it yet. But let's avoid dealing with the product by multiplying this out. So this is all about manipulating the algebra before we take the derivative so we can use the sum and difference rules. So f of w, when I distribute or FOIL, I get w squared. The outer is plus 8, and the inner is minus 3, giving me plus 5w minus 12. And so now if I want to take the derivative of this expression, the derivative of 2w squared is 4w. The derivative of a positive 5w is just plus 5. So we had a product, but we rewrote it by multiplying out, and then we could use the sum and difference rules. The next example is an example where we have a quotient, and again, we haven't gone over the properties for taking the derivative of a quotient, and it's not the same as the quotient of the derivatives. So what I need to do is again use algebra to rewrite this. And we'd rewrite each term over x. We would simplify, then we'd take the derivative. So I get 5x squared plus 8x minus 1. Now I can take the derivative of this function individually, but the derivative of 5x squared is going to be 10x to the 1 plus the derivative of 8x is just 8. The derivative of negative 1 is 0, so I don't need it in there. We have one last one where we have to manipulate. We've got f of x equals x squared minus 1 over 1. We're going to rewrite this as f of x equals, let's factor it first. We get x plus 1 times x minus 1 all over x plus 1. We can cancel the x plus 1, so we've got a simplified version. We've got x minus 1. I'm going to write the domain though. I know that x cannot equal negative 1 because the original function had that factor of x plus 1. So I know that x equals negative 1 isn't in the domain, but my new function is f of x equals x minus 1. And I take the derivative of that. The derivative of x minus 1, well, the derivative of x is 1. The derivative of 0, the derivative of negative 1 is 0. So the derivative of this, what appeared to be a really complicated function, is really just the slope of a line, which is 1. And that line has a hole in it, but that's okay. Let's look at some higher order derivatives. And higher order derivatives just means you're going to take a derivative more than once. And so there's some different notation. We've got the derivative of a first derivative, f prime, would be f double prime. That's considered a second derivative. Another notation for that is to put the 2 in, instead of using the double apostrophe, we just do f with a 2 in parentheses. That you don't use that often. You use it once it gets higher than 2 generally. The other notation is d squared y over dx squared. It means take the second derivative of y with respect to x. If we want to find the third derivative of f of x equals 3x cubed minus 5x plus 12, the first derivative would be 3 times 3, which is 9x squared, minus 5. We take the derivative of negative 5x, which is negative 5. The derivative of the constant is 0. If I want to take the next derivative, that would be the second derivative. That would be 2 times 9, which is 18x. And the derivative of the negative 5 is 0. I want to take one more derivative, and that's just going to be 18. So having a higher order derivative just means to take the derivative more than once. The last example in this video has to do with horizontal tangents, and the question says, at what values of x does the function f of x equals x cubed minus 3x plus 4 have horizontal tangents? And so what we would do, that's the same thing as asking where does f prime of x equal 0? And so what we would do is we would first find f prime of x, first find our derivative, which would be 3x squared minus 3. And to find out where the derivative would equal 0, we would just take the derivative and set it equal to 0 and solve. So to find the x values for which a function has a horizontal tangent, you take the derivative and you set it equal to 0. So we can factor out a 3, gives us x squared minus 1. That's equal to 3 times x plus 1 times x minus 1 would equal 0. So we have horizontal tangents at x equals negative 1 and at x equals positive 1. And let's double check by pulling this up on the calculator. So I'm going to graph the original function, the x cubed minus 3x plus 4. I'm going to do a zoom 6 to start with and see if I get the pieces that I need in there. And it looks like I have. We know that we have horizontal tangents at either a max or a min. And if I trace, since we said one occurred at negative 1, I'm going to trace on negative 1. And you can see that that occurs at a maximum value. It makes sense that there is a horizontal tangent there. Let's trace on 1 and hit enter, and you can see there I would have a horizontal tangent there. So now you're not always going to have a calculator obviously on both parts of the test, but when you're first learning how to do this, it's a good idea to graph it, get a visual, and it does make sense that we've got horizontal tangents at those values. Now, if you want to find out over what intervals is the slope of f of x positive or negative, and you don't have a graphing calculator with you, we're going to use a sign chart. And so we know that f of x is equal to 3 times x, f prime of x, excuse me, the derivative function, 3 times x plus 1 times x minus 1. We know that. I'm leaving it factored. And I want to find out the SIGN of f prime. And so I take where f prime is equal to 0, which is negative 1 and 1, and I find test values, just like we did before when we were dealing with the domain of, say, a radical function. And I substitute these values into the derivative. I want to find out where the derivative is positive and where the derivative is negative, so I'm plugging these values in the derivative. When I put a negative 2 in for x plus 1, I get a negative. And when I put a negative 2 in for x minus 1, I get a negative. So a negative times a negative is a positive. When I put 0 in for x plus 1, I get positive. And for x minus 1, I get a negative. A positive times a negative is a negative. When I put a 2 in, I get a positive for both factors. So I now have a nice sign chart that tells me the intervals over which this function is, with the slope of the function is positive or negative. F prime of x is greater than 0, or the slope of the original function is positive from negative infinity to negative 1 and from 1 to infinity. And the slope of the original function f of x is negative, or f prime of x is negative, from negative 1 to 1. And so we've already graphed this function, so let's pull it back up again and confirm our intervals here. We said when the function is increasing, the slopes are positive, so this is increasing from negative infinity to negative 1. It is increasing again from 1 to infinity, and then you can see from negative 1 to 1, the function is decreasing. So in calculus, we use our graphing calculator sometimes to make a conjecture, and we use the analytical work to confirm it. Sometimes we do the analytical work and we use the graphing calculator to confirm that our analytical work makes sense. But it's nice to have a visual, look at something graphically, along with looking at it analytically. Okay, I'm going to end this video here.